Hi, I'm Mrs. Rutchling, and this is Chapter 3, Matter and Energy. A basic definition of matter is anything that occupies space and has mass. Occupies space means volume, and chemists are interested in matter and how it relates to its atoms and its molecules. We can look at the overall picture, or what we can see, the macroscopic world, to understand the particulate microscopic worlds we can't see. And then we use symbols as a language to describe this. For our macro, we have water and ice and also water in the air. For the particulate, we can see here is a solid, a liquid, and a gas. And over here we have the symbols. All of the symbols are the same. The only thing that's different is the designation of the state, gas, liquid, or solid. Some more basic definitions. Atoms, all matter is made up of atoms, and some things we have just those atoms. An example here is aluminum, and we see that if we look at the aluminum, it is only made up of aluminum atoms. But we also have molecules, which are any two or more atoms bonded together. And so here's an example of rubbing alcohol, and it has several atoms that are bonded together. We can also have molecules that have the same. We also have molecules that have the same atom bonded together. If we look at the kinetic molecular theory, and sometimes you will see this abbreviated KMT, is that the atoms and molecules that make up matter are in constant motion. Even in a solid, the particles are vibrating. If we look at our states of matter, the forces of attraction between the particles will determine the state. Our solids have a very rigid shape and the volume is fixed. If you look at the external shape, it can reflect the external shape can reflect the particulate arrangement, the atoms and the molecules. They usually have a regular pattern, they vibrate in place, and they have a lowest amount of energy of the types that we're talking about. The liquids, and we see our abbreviation solid for S, liquid, that's supposed to be an L. They have no fixed shape, but they have a fixed volume. They don't fill the container completely, and they have enough energy to flow. Gases have enough energy to completely overcome those forces of attraction, so they completely separate. They have high energy, they're far apart and moving quickly. Our animation shows us that even the solids are slightly vibrating here. The liquid have enough energy to slightly overcome, and the gas has enough energy to completely overcome the attractive forces. Speaking of gases, gases are compressible because the particles, the atoms or the molecules, are not in contact with each other. There is space or air between them. You can press those particles together. Two states of matter you might not be familiar with. The first is plasma. It has so much energy that the electrons are completely stripped away and it has an electrical charge. The sun or stars are made of plasma. Plasma TVs actually have a very thin layer of plasma between two pieces of glass. The existence of plasma was predicted almost 100 years ago, but it was first artificially created in 1995. Other state of matter that is probably new to you is the Bose-Einstein condensate. So when atoms are cooled to near absolute zero.
This condensate was first proposed by Nagendra Bhatt Bose when he wrote a letter to Einstein. Einstein was so impressed he completely translated and then submitted the paper to a journal for Bose.
I'm about to meet a scientist who can't be bothered with hundredths or even thousandths of a degree for that matter, aka a millikelvin.
We are bored by millikelvin. We like to go to nanokelvin. That is
Nanokelvin?
Nanokelvin. That would be a billionth of a degree.
A billionth of
absolute zero. It's very, very cold. It's a million times colder than interstellar space.
It's just about the lowest temperature ever reached. A place so clear and cold, physicists can see the fundamental laws of nature in action. MIT's Martin Zwierlein is going to use sodium atoms to show me how to get there, the final frontier of cold. Wow. And so how do you do that?
So we can start over there at the oven.
The oven? Step 1, cook up some sodium atoms, the same kind in your table salt, to about 700 degrees Fahrenheit. That way you can separate them.
You want to get single atoms to play with, single sodium atoms, lots of them, a whole stream of them.
Step 2, hit them with lasers. I know you MIT guys have the reputation of being very smart, but I have a little tip for you. Lasers are hot. You might be a little backwards there.
Yeah, you might think about Star Trek where they kill people with lasers. Turns out here, we cool atoms down with lasers, and they get a recoil from it. Just if you hit a billiard ball with another billiard ball.
In other words, when you hit atoms with just the right amount of laser light, it acts like a little shove in the opposite direction that the atom is moving, slowing it down.
If you look down here, you will actually see the cold cloud right there in the center of the vacuum chamber.
So that glowing star thing? It looks like the sun. It ought to be super, super hot.
No, it's actually extremely cold. Those are 1 billion atoms cooled to a millikelvin.
1,000th of a degree above absolute zero. But lasers can get us only so far.
You cannot reach the nanokelvin temperatures just with laser cooling. So we need another technique.
Which brings us to step 3. Get out your coffee cup.
What takes over after laser cooling is what we call evaporative cooling. It's the same thing that happens to your coffee right now, because it's just cooling down. So if you now force it a little bit by blowing on the coffee, you speed that process up. The coffee gets cold more quickly. That's exactly what we do here.
But instead of a coffee cup, Svirline uses a cup made of magnetic fields to trap his atoms. Then he blows on it with radiation and lowers the rim of the cup to let the hotter atoms escape.
So now we're going to do this coffee cup cooling. It's going to bring us to nanokelvin. Okay, ready for this?
Yes.
Let's do this.
All right.
So, can you please switch on this stuff? Do this. This is great. Let's switch on this guy. And then this awesome knob here.
Press the awesome white button.
Fantastic. So that's good. Please press F12.
Always wondered what F12 does.
So you see now the atoms are cooling because the cloud size gets smaller and smaller and smaller. And here you see the temperature drop.
Oh, wow. It takes a few minutes, but eventually the atoms become so cold, they lose their individual identities altogether and coalesce into that new state of matter called a Bose-Einstein condensate. Wait a minute. Okay, so
Yes,
that's the condensate?
That's the condensate.
But look at the temperature.
Yeah, it's very cold.
177 billion.
Billionth of a degree.
177 billionths of a degree Kelvin.
This is the coldest spot in the universe right now.
That's
right
amazing.
here.
So not even in outer space.
No. Outer space is 1,000,000 times hotter.
Not the dark side of the moon,
No, it's like all hot.
comets,
Terrible, yeah.
black holes, nothing. This is it in this room.
Yes.
That's amazing. I would ask its autograph if I could. But it's not about setting obscure records. What Svirline is excited about is what these exotic states of matter can teach us about the universe.
Our puff of gas teaches us about the neutron stars. Or, split second after the Big Bang, there was this weird form of matter called a quark gluon plasma.
A super hot type of matter in the early universe that would give rise to everything we see today. So you're telling me that this tiny, freezing cold dot can teach us something about enormous, blazing hot stuff.
That's the fun part of physics. It connects these very different areas. The very hot, very cold, everything is governed by the same laws.
Amazingly, what happens at these ultra-cold temperatures is that atoms get so smeared out, their waves start looking indistinguishable from those of super-hot particles under extreme pressure. Like those inside the inner core of neutron stars. So dense, a teaspoon of them weighs 10 billion tons. Svirline and others can now simulate substances like this in their labs and probe their mysteries. That's incredible! And then in a couple more years, you'll finally do it. You'll hit 0.0, absolute zero, and we'll be done.
Yeah, unfortunately, it's never possible to reach absolute zero.
What?
You know, there's always going to be a little drop of energy sitting around somewhere.
Turns out it's impossible to get to absolute zero because no matter how cold you get, everything has tiny quantum jitters. And where you have motion, even a tiny amount you have heat. But that's not stopping scientists from getting even colder to explore the fundamental laws of nature and how our universe came to be.
Just the way noise can drown out music, heat is like the noise that obscures things. If you get things really, really cold, you sort of drown out, you damp down all the noise, and you can listen to what nature is whispering to you.
If we look at terms of energy, the Bose-Einstein condensate, because it is so cold, has very little energy. Next, the solid has a little bit more. Remember, we say those particles vibrate. Liquid has enough energy to slightly overcome the attractive forces, and so it can flow around. Gas has enough energy to completely separate, so it spreads out. And then plasma has so much energy that it actually gets rid of some of its electrons. If we're thinking of absolute zero in this temperature scale, the temperature in space is about 3 degrees. In this Kelvin temperature scale, water would freeze at 273 and water would boil at 373.
We're going to start with types of solids, and we're going to separate them into two types of solids. Amorphous means there's no particular arrangement. They're just kind of clumped together, a hot mess. So rubber and wax. And then we also have crystalline solids, which are highly ordered and they're in a pattern. So for example, here we have silicon dioxide, so 1 silicon and 2 oxygen. And here those molecules are in an ordered arrangement, and so it's a crystal, quartz, a rock. On the right, we have the same molecule, but they're just all clumped together, and this is how you make glass. You take sand, heat it up. You can see here also a different representation. There's no order. And with the crystalline solid, we have this nice 3D structure. If we're talking about crystalline solids, if we look a little closer, they have a crystal lattice. If you have ever seen a lattice that roses or flowers grow onto, a crystal lattice is just a 3D arrangement of the particles, and it's very similar. So we can look at a coordinate system if we'd like to. You can see we have, this would be 0, 0, 0, 1. 1, 1. So you can make coordinates like a graph for all of these. And then the very smallest shape that still has the structure is called the unit cell. Here's a summary of our solid, liquid, gas properties. We said that a solid is going to vibrate around. They cannot be compressed. A liquid, the particles are free to flow. They're very close together, but because they can flow, their shape is not definite. And finally, a gas has enough energy to completely separate. What state of matter does this picture represent? Because there are some spaces here, I'm going to call this a liquid. Here, there is no definite structure. The particles are spread out, fill the entire space, so I'm going to call that a gas.